interesting aspects about our universe. The first is that the universe is homogeneous and isotropic over large scales. You see, if you talk to a biologist or a zoologist, the person will say, suppose you take a rat. Okay? You talk to somebody else, there will be some standard thing. Like that, you talk to a cosmologist, on the first words the person will utter is homogeneous and isotropic, and they have done that. Okay? So the universe is homogeneous and isotropic. However, this needs some kind of an explanation. We see that we have, Earth, Sun, and so on, and in our neighborhood, the universe is far from being homogeneous and isotropic. Okay, so we need to quantify what do we mean by this. And one of the standard examples which I give for this is the following. Suppose you look at a well-maintained lawn, a green lawn. When you say it is well-maintained, what you mean is that broadly the greenery is uniform throughout. Okay? Now you ask a grasshopper, and the grasshopper will look at you saying that you have gone mad, because grasshopper does not look at it as a well-maintained lawn. What is the difference between the perception of a grasshopper and your perception? The perception lies in what scales you are looking at it. Suppose there is an insect sitting in the lawn. The insect is comparing the greenery of say 1 inch by 1 inch here, where there is a grassless patch, with another 1 inch by 1 inch where there is a lot of grass. So the insect will say that it is not uniform at all. Whereas when you are looking at the lawn, at the back of the mind, what you are doing something like, you are taking a 1 meter by 1 meter, averaging the greenery, another 1 meter by 1 meter, averaging greenery, and comparing the average greenery in both these things. So on this average greenery is same from one meter square to another 1 meter square. So when you say something is uniform, it has to be qualified by the fact over what scales it is uniform. So when we say homogeneous universe, if we are going to look at things like within our galaxy or the neighborhood of galaxy, it is like a grasshopper looking at the lawn. When we say homogeneous and isotropic on cosmological context, what we mean is over scales of about 100 megaparsecs, the universe is homogeneous and isotropic. It means that suppose you were to divide the universe into cubes of 100 megaparsec size, average the density in each of these cubes, and compare this average density from one cube to another, then this average density remains same from one cube to another. That is what we mean by saying it is homogeneous over scales of about 100 megaparsecs. So this is the first aspect of the universe which is striking. Another aspect about the universe is that we have within this framework of homogeneous isotropic universe, we have structures over various scales. Broadly, these structures can be categorized into two types. One is, say, planets, stars, galaxies, etc. And second is clusters of galaxies and larger. Now, the reason why one has divided it into these two is a specific reason for it. And the reason is that the physics of their formation is qualitatively different for these two cases. When you talk about planets, stars and galaxies, etc., the physics of formation primarily involves gravity plus various other physical processes like fluid dynamics and so on. Whereas when you are going to talk about clusters of galaxies and larger, the physics of their formation is primarily through gravity, with other forces like fluid dynamics and all playing a very minor role. And so these are categorized under the thing of large scale structures. Who talked about, somebody talked about large scale structures, right? It's not yet over, huh? Okay. Oh, actually, it's not yet over. Now, in the context of microwave background, it is these things, large scale structures, which are of basic importance. Okay. These will not be, these are not the things which generally will have any imprint on the microwave background. The third important, interesting aspect about our universe is, of course, the microwave background itself. Okay. So let me, okay. So third, same. Now, we are immersed, Jayanti talked about CMBR data analysis, right? Jayanti Prasad. Okay. So we are immersed in a, so how much of did you think we cover in background CMB physics? Did we cover it? Or mainly it was on data analysis techniques? Okay. So, okay, so we seem to be immersed in a radiation which is coming to us from all directions. The characteristics of this radiation is the following. First of all, it seems to be the same from all directions, and so it is called a background. This radiation has a black body spectrum, and the and in this black body spectrum, this the black body spectrum I mean it is corresponds to a temperature of about 2.73 Kelvin, and if you using Wien's displacement law, if you look at the maximum the wavelength of the maximum peak of the black body spectrum, that falls under the microwave region, and hence the microwave, and it is radiation, and so radiation. These three portions, the microwave, background and radiation, are observational features. There are no two opinions about it, that they are observed and you see them. However, the cosmic part is at the level of inference. There are theories in which they try to explain the microwave background without any cosmological origin. However, that is extremely difficult, and one has to have very contrived models to do that. And so most of the time when you talk about microwave background, most of the time you refer to it with the cosmological context, and that is why the cosmic microwave background radiation. Now, I mean, this of course you must have read it several times about how it was discovered. That you see, what happened was there were these two people who had nothing to do with physics. Okay, their parents told them, take engineering, don't take physics, you will starve otherwise, and they went into engineering, and they became radiophysicists, and they were using an antenna which was abandoned after the Second World War, and they were trying to calibrate it, and they found that there was they could do it completely, except they had some noise which was coming in there, and they were very unhappy with themselves. Probably their boss told them that they don't know how to do experiments, and they tried to do cleaning, various things, nothing worked. But there are two characteristics of that. One was that it is of intrinsic nature. There is something which is sticking on that, and because you move it in any direction, it was the same, or it was coming from outside. And they tried to clean it and various other things. Nothing happened. I am not sure, but I heard that when they published their paper, they just called it anomalous noise in radio antenna. Is it today? Of course, at the drop of the shot, they will say, I have discovered a new particle. Okay? Nothing like that. They were very conservative in what they said. Anomalous signals in radio antenna. Okay, this was their paper. And the story goes that before they published it, they communicated with Peebles and Dickey, who were also onto this. And I think the papers were published back to back. First there was this anomalous radiation, then Peebles and Dickey as to what is the source of it. This is how it was discovered. And 65, and they got the Nobel Prize in 78. Okay, so that was the, probably that was one of the first Nobel Prize for cosmological context. I think. It's nothing else. Was there anything else before? I don't think so. Why cosmology? Even astrophysics was, I think that was the first. Okay. Yeah, so this is the story of the microwave background. Now, the interesting thing about the microwave background is the following, that for reasons which I will describe, microwave background has imprinted in it signals of a very early universe. Okay? And it is one of those things which is least spoiled by evolution in future. So in some sense, it carries an information when the universe was around 700,000 years old. Okay? Right till here with hardly any modification. So it has, okay, so it is of pristine nature. And so these two things which I described, both the homogeneous and isotropic evolution of the overall universe, as well as the large-scale structures, both have their own imprints on the microwave background. Now, any radiation has three characteristics. One is its directional dependence, which is the anisotropy. The other is polarization. Okay? And the third is the spectrum. Now, CMB physics deals with all three of those. It so happens that anisotropy, there has been a lot of progress in terms of observation. In polarization, it is more difficult to observe, so it started late and results are coming in now. As far as the distortion of the spectrum is concerned, it is found to be black body to a very high degree. Okay? And one has not seen any deviation from the black body spectrum, except when it passes through a cluster of galaxies and so on, which I will describe. Okay. So let us look at the homogeneous universe first. And as I think Prasoon must have described, the homogeneous universe is governed by what is called a Robertson-Walker line element. And the metric for a Robertson-Walker line element is given by minus t square plus a square dr square by 1 minus kr square plus r square d omega square. So this is the most general form of the Robertson-Walker universe, and this is the most general form of the line element for a homogeneous isotropic universe. There is this fellow sitting here, which is k equal to 0 or plus minus 1, and this basically refers to the nature of geometry of a constant time hypersurface. That is, at a particular time, how does the surface look like, hypersurface look like? Just to give you an example, if suppose you have a sphere, suppose instead of the 1 plus 3 dimensional universe, you are talking about a 1 plus 2 dimensional universe, okay? Then k equal to plus 1 will be something like a sphere expanding or contracting in 3 dimensions. So, and this quantity A, which is a function of time, will play the role of the radius of that sphere. Okay. In fact, this can be written in a different way, which is minus dt square plus a square t into a quantity d chi square plus sk square r square d omega square. Where sk square has the following form. If k equal to 0, this sk is a function of chi. If k equal to 0, s of k equal to chi itself. So in other words, k equal to 0, s of k is Cartesian, the three-dimensional flat space described in spherical polar coordinates. If k equal to +1, then sk will be equal to sine of chi. Okay? Now if you look at it, this is sine square chi. So in some sense, you have this d omega square, which is d theta square plus sine square theta d phi square. And if my d phi now takes the, if d omega takes the role of d phi, now this is again that kind of a structure, d chi square plus sine square phi d omega square. Okay? So this and this refers, so just like if you for a given chi, this refers to the surface of a sphere. Okay? Because if for a given chi, it is chi square d theta square plus chi square sine square theta d phi square. So that refers to a sphere. So like that, this thing refers to a kind of a hypersphere because the structure is exactly the same. Okay? And these are called positive curvature surfaces. And these are zero curvature surfaces. And as I said, this is something like a sphere whose radius is changing with time. And this is something like a three-dimensional generalization of a flat rubber sheet which is expanding or contracting with time. Okay? That is, at a constant time, the surface is just flat space. Okay? So like that, in this case, at a constant time, the hypersurface is just the Cartesian space. These two have an analogy with 1 plus 2 dimension. As I said, this corresponds to a rubber sheet. This corresponds to an expanding or contracting sheet. The case of k equal to -1 is different. In the case of k equal to -1, sk equal to sine hyperbolic chi. Okay. Now, this refers to a constant time hypersurface which has this uniform negative curvature everywhere. Now the question is, just like the previous case of rubber sheet and sphere, you may ask, what is the analogy of this? You do not have an analogy in 1 plus 2 dimension for a surface which has constant negative curvature. For positive curvature, you have a sphere. For zero curvature, you have a rubber sheet. But for negative curvature, you do not have such an analogy. Okay? So these are negative curvature surfaces. And it turns out that if you calculate the total volume of the universe, okay, just like when you have a sphere, suppose you have a rubber sheet. What is the total area of the rubber sheet? Think of it. Huh? The rubber sheet, yeah, homogeneous isotropic rubber sheet is infinite. Okay, when I'm asking you a question offhand, you should be smart enough to guess it will be 0 or infinite. That's what I will ask you. Okay. Okay, so that is infinite. If I have a sphere, okay, it is a finite area. Now, so the interesting thing is, suppose somebody says, I have a finite area of plot. You will say, what is a boundary like? Okay, but if one owns the entire Earth's surface, it's a finite area without a boundary. So the sphere, surface of a sphere is a finite area without a boundary. Okay. Similarly, for a closed universe, like for the k equal to +1 universe, the positive curvature universe, it has a finite volume without a bounding surface. Okay? And it turns out, so this is finite volume, so you call this a closed universe. This is called a flat universe, and this is called an open universe because the total volume is infinite. There is a way I usually like to write this SK as, which of course mathematicians become very unhappy with me, because okay, so you can say that S of k can be written as sine of square root of k chi by square root of k. Okay, I also tell you why mathematicians will be unhappy. If k equal to 1, it's all finally sine chi. If k equal to -1, we just find this sine I of chi, this I versus sine hyperbolic chi. The problem is what you do with k equal to 0. There you irritate the mathematicians. You say, okay, I will not use k as a discrete thing. I will take it as something which is tending to 0. Okay? And so this will be root k into chi, this will be root k cancels and get chi. Okay? So we get all the three results by being non-rigorous. Okay? So this is a good way of remembering what is the sign of cos. Okay? Yes. Okay, so these are, so this is how you categorize this, the universe. And then, so once you have this, you have your metric tensor. And your metric tensor is equal to -1 a square, sorry, a square 1 minus k r square, a square sine square theta. So this is your metric tensor. Once you have this metric tensor, you can calculate all your gamma, everything, and then substitute it in the Einstein's equation, g mu nu equal to -8 pi g t mu nu. Okay? So using this, I can calculate these components, and for the t mu nu, the mixed tensor t mu nu for the case of cosmology will be given for a homogeneous isotropic case, will be given by minus rho p p e 0. This is the form of, so it means that you are connecting the pressure and density to geometry, which is what is the aim of Einstein's equation. So you have the following equations, which are called the FRW equations. And when you say connecting metric to these, it basically means connecting these parameters, this parameter scale factor A to these things. So the two equations which you have is a dot square by a square plus k a square equal to 8 pi g by 3 times rho. And I will follow the bad habit of using c equal to 1. Okay, so 2a double dot by a plus a dot square plus k by a square equal to minus 8 pi g times. Actually, these are actually 3 equations, but all 3 equations repeated because all 3 directions are the same. Okay. So this is what we have, and this has to be supplemented by a relationship between rho and p. Okay. And this is what is called the equation of state. Okay. So I have to have p as a function of rho. Okay. Now before this, what is the physical significance of scale factor? I mean, often one says scale factor is the size of the universe. That is nonsense. There is nothing like size of the universe. Suppose you have a uniform rubber sheet, there is nothing like size of the rubber sheet. Scale factor is a parameter which is a measure of the typical distance between points. So what has relevance is the not the absolute value of scale factor, but the ratio of scale factor at 2 times. Okay. So it is only the logarithmic increase of scale factor which has a physical significance, which is the Hubble parameter, A dot by A. A as such, the absolute value of A is not of relevance. So often what one does is, one normalizes A to be A equal to 1 to A. Since it's absolute, I mean, just like in the Schrodinger equation, you know, phase doesn't matter, you put phase equal to 1. It's just like that. If something is not measurable, you can choose what you want. Okay. So that is about the scale factor, and this is the equation of state. Once you have put in the equation of state, okay, then this can be solved to derive a relationship between the scale factor and time. Okay, and okay. So suppose we have in the era in the very early era, when the universe is radiation dominated, then 3 is just rho by 3, and you put rho by 3 here, And the result which you get for such a situation is for P equal to rho by 3, we have, oh no, sorry, before that we need to do one more thing. Okay, so now in addition to these two equations which I gave you, there is one more equation which is the continuity equation. Okay, and the continuity equation is T mu nu covariant mu equal to 0, which in our case of a special case of the diagonal T mu nu in the form, it comes out to be d of rho a cube plus P d a cube equal to 0. Okay, we putting in this form of the form for. So then we have, in addition, we had the a dot square by a square equation and a double dot by a equation. Okay. Now, one thing about this is, which might have been mentioned, I don't know, in the earlier talk, is that this actually is a very simple equation, just the first law of thermodynamics. Okay. Basically, what it says is, I said A is a measure of the typical length of the 2 points in the universe. So, suppose you make a cube, okay, of something proportional to A. Okay, then this A cube will be proportional to the volume. Now, this is energy density, so this is proportional to the total energy in that volume. Okay. Now, what does the conservation of energy say? Conservation of energy does not say d equal to 0. Often people sort of so what it says is d is the work done. Okay, so this is dE. This is P into this is dV. So this basically says du plus P dV equal to 0, which is the first law of thermodynamics. Okay, and it is understandable because first law of thermodynamics is nothing but energy conservation, and that is exactly what is continuity equation for T mu. Okay, that is how it has this connection. Okay. Now we have these three equations. Now one thing one has to be careful about these equations. These three equations are not independent. Okay. However, it is not like, three equations in two variables. See, when you have, say, three, suppose you have algebraic equations in two variables, and you have three equations, linear algebraic equations in two variables, and three equations, then you say that you can choose any of those. Okay? The situation is not similar here. There is a fundamental difference between this and the other. And the fundamental difference is the following. You see, this is a dynamical equation, whereas this is a constraint equation. Okay. So the solution to the dynamical equations should be such that they obey the constraint equation. So what you can do is you can actually go. You can take these two equations and derive this. Okay, and then take these two equations and derive this. But you can't take these two equations and derive this, because this equation is a constraint equation. Okay, a constraint equation cannot be derived. Okay. So now you take two of these equations and you supplement it by this one. And it is always easier, to choose these two equations and supplement it by the equation of state. So what you do is you substitute this equation of state over here, P equal to rho, and you will get rho proportional to 1 by A4. Okay. And if you substitute this rho over here, for the case of k equal to 0, you will get A proportional to T to the power half. So if you have universe which is dominated by radiation, its evolution will go as T to the power half. So this is the thing which goes into. Similarly, if you take pure matter, which is P equal to 0, then this turns out to be rho equal to 1 by A cube. Okay, and this will turn out to be A proportional to T to the power 2 by 3. Now here about rho going as 1 by A4, I'm sorry if I'm repeating something which you told in earlier classes, so I exactly do not know what was done so. See here, one can look at it this way. this rho is like the number density into hd. Okay, that is the number density of photons into the hd of the photon, so it's the total energy density. Now the number density of anything by its definition goes down as 1 by volume, and hence this number density goes down as 1 by volume. Now for the case of dust, the only energy density is the rest mass energy of particles. Now the rest mass energy of individual particles does not change with the expansion. Okay, so a better way I can write it down as the number of density of particles times E, which is the energy of each particle. Okay. For the case of matter, number density, like any number density, will go as 1 by AQ. Whereas this energy comes purely from the rest mass energy. That is, now E square equal to P square plus M square, and P is 0 for the particles at rest, for dust. So it is coming only from M, which is a constant. So it means that the E does not evolve, which means the total energy density goes as 1 by AQ. That is what I was mentioning for the case of P equal to 0. That, okay, that rho will go as 1 by AQ. In the case of photons, what happens? This number density, like any other number density, goes as 1 by AQ. However, since photons are zero mass particles, okay, the E square for photons equal to M square, which is 0, plus P square, I mean C equal to 1, okay? And so E square will go as P, and P goes as 1 by A. I mean, if you write the geodesic equation in GTR, P will go as 1 by A. So this will go as 1 by A square, so E will go as 1 by E, since E square goes 1 by A square. So in the case of photons, there is a 1 by AQ coming from M and a 1 by A coming from E, and that together comes as 1 by A4, and that is why for radiation the energy density goes 1 by A4. So this is the physical origin of why that 1 by A4 comes in rho, whereas 1 by AQ comes in dust. Okay. Okay. And so depending on how rho evolves, you have whether A goes as T power half, as in the case of radiation, or T power 2 by 3 in the case of ordinary pressureless matter. Okay, fine. So now, since we are going to focus on CMVR, we will look at the case of rho going as 1 by A4 in further detail. There are, shortly I will come to it, there are reasons why the photons are coupled very significantly to the matter in the universe. Okay, now what is the implication? Yeah.
So radiation density will in general always be.
Which I will come to maybe today, later, or tomorrow. Why the radiation in the universe interacts significantly with the matter in the universe in our universe. Okay. So now, what is the implication of this? You see, if suppose you take a cylinder and put in, say, oxygen molecules selectively with same energy. You leave it for some time and then you look at the energy distribution, it won't remain same. Because of collisions, the distribution will change. And you know from statistical mechanics that it will tend to reach an equilibrium distribution where the distribution is governed by the Maxwell-Boltzmann distribution. So in other words, Maxwell-Boltzmann distribution is an equilibrium distribution with which molecules of gas tend to. Similarly, if I take a chamber and put in photons all of the same energy, then these photons will be interacting with the walls of the container, exchanging energy, and in the photons even the number is not conserved, unlike molecules. Okay, so exchanging energy till a situation where the distribution of photons will reach a steady state. Just like what is Maxwell-Boltzmann distribution is for gas molecules, the blackbody distribution is for photons. So because it reaches an equilibrium, the photons, if there is sufficient interaction, then these photons will reach an equilibrium distribution, which is a blackbody distribution, which is a Planck spectrum. So these photons have a Planck spectrum. Now you know that for a blackbody distribution, from Stefan-Boltzmann law, the intensity is proportional to T to the power 4. Okay, and what is intensity? And intensity divided by C equal to the energy density. So that is also proportional to T to the power 2. Okay. So what does this mean? The total energy density goes as 1 by A4. The total energy density goes as T4. It means the temperature of the radiation goes as 1 by A. Okay. I will derive this again by another way using the Boltzmann equation later, before I go over to perturbations. But so this is a result you can actually arrive by just simple argument. The immediate implication of this is that when the value of A was small in the universe, the temperature of the universe is very high. When it becomes large, it drops. Now I also know that A goes as T power half or T power 2 by 3, depending on whether radiation dominated or matter dominated. In general, for most of the kind of normal matter, unlike dark matter and dark energy and so on, A will always go as T power n less than 1. Okay, but greater than 0. Okay. So it means that A is always a monotonically increasing function of T, but it does not increase linearly, it increases more slowly. It means that a small a implies an earlier time. Okay. Because a increases, so a smaller a means earlier time, small t. It means that t is proportional to time to the power minus n, where n is a positive number, because it is greater than 0. And hence, in the early universe, the temperature of the universe is very high. Now, this okay, it is this which has very deep bearing on the CMB physics. Now, since the temperature is very high, now look at it in the following way. Now you have, suppose in the laboratory, you have molecules or atoms, and I heat it, okay, the cylinder, okay. So basically, there is high energy radiation which is inside the black body spectrum. If it is high enough energy, these photons will ionize the matter. Once the matter is ionized, then you do not have the individual basic units are no more neutral particles, but they are all charged particles, electrons and nuclei. Charged particles interact very strongly with radiation, and hence radiation and these particles keep on getting scattered. It is this scattering which leads to the equilibrating condition which leads to black body. You see, in order to have a black body, you have to have equilibrium. In order to have equilibrium, if suppose you start from an arbitrary state and you reach an equilibrium state, you need to have scattering. It is the fact that at high energy photons ionize the matter, and ionized matter interacts very strongly with radiation. It is this fact which ensures that the radiation, quite independent of what it started out, will reach an equilibrium distribution, and that gives a post priori justification of why we take it to be a black body radiation. Now, however, as the universe is expanding, what is simultaneously happening is the following, that this density and hence the temperature is also decreasing with time. Okay? So, at the early phase of the universe, since it undergoes scattering, a photon will not be able to carry information for long distance coherently. Why? It is like, suppose you have Brownian motion. So in Brownian motion, what happens? Lycopodium powder, the standard experiment, it keeps on having the zigzag motion. Why? Because of random hits with other molecules. The same thing happens here. The photon goes in one direction, interacts with a particle. Okay. Now in those energies, unless you have very high energies, the scattering is independent of the direction. It means the direction in which the photon gets scattered is independent of which direction it came from. So what we call in statistical mechanics a Markov process. The photon does not have any memory. It does not know from where it came. Okay? It is equal probability to get scattered in any direction. Now it gets scattered in a particular direction, moves some distance, again gets scattered. So in other words, the path of the photon is something like, when you see something through thick fog. Because of increasing interaction, the information is lost. For example, if suppose I have a dot and I see it through fog, what happens? Suppose there are 1,000 photons coming here. Okay? Some will get scattered here, some will get scattered, some will not get scattered. So what will happen is, this dot will get smudged into a kind of a circular region. So if you have a pattern and that gets smudged, you basically have mixing, which basically means that the information is being lost. Okay? So when these photons are traveling through the universe during the time when the universe was ionized, then any information contained carried by this photon gets smudged because of this scattering. However, when the temperature, in a very oversimplified model, suppose you say that all the atoms in the universe are made of hydrogen, suppose. Then when the photon reaches around a temperature corresponding to the ionization energy of hydrogen, then what happens is, see at a microphysical level, how does it operate? You have an electron and a proton, okay? They tend to come together to form hydrogen, but there is a photon of sufficiently high energy. It hits it and dissociates it. So that is why neutral atoms cannot be sustained. But once the average energy of the photon has gone below the ionization threshold of hydrogen, once this forms a neutral atom, the photon no more has enough energy to dissociate it. Okay? And it becomes a neutral atom. Once it becomes a neutral atom, then photon no more gets affected by the matter in the universe, because neutral photon does not have significant interaction or scattering from neutral matter. Okay. So at a later time, the universe undergoes a transition from ionized matter to neutral matter, and simultaneously with it, the photon, as one puts it, decouples from the rest of the matter of the universe. Okay, but there is something which one should mention about the nature of this transition. Okay, if suppose the equation that governs this transition from ionized matter to neutral matter goes by the name of the person under whom your institute is named, which is Saha ionization equation. Okay, and so that is, suppose I have x is the degree of ionization, then it goes as 1 by x equal to some constant t power 3 by 2 e to the power ionization energy by kT. These are the important things here. Others are all uncommon. Okay. So this is how it goes. Now what happens is, one would have expected that because this is a e to the power exponential, so if suppose you draw the degree of ionization with temperature, okay, one would say from large temperature it starts and slowly it goes down. That doesn't happen because of the structure of this equation here. The transition is not smooth. And that is what helps us to identify an epoch of transition in a very unambiguous way. At very high temperature, the ionization is almost 100%. So X equal to 1. At late times, it is very small. I mean, there are reasons why it not goes to 0, but it goes to about 10 to the power minus 4. Okay? But this transition from 1 to 10 to the minus 4 is not something very smooth. It actually happens at a fairly narrow range of temperature. And that is why you can roughly identify a particular temperature as a transition temperature. Okay, and this transition temperature is about 3000 Kelvin. Okay, and the matter before, so since I know that temperature goes as time to the power minus n, I can write a similar thing with respect to time and saying that this is my degree of ionization, this is time, it is almost 100% ionization and sharply drops to some level. And this is the epoch of ionization. Okay? And before this epoch, the universe was ionized. After this epoch, it was, or rather, much before this epoch, the universe was completely ionized. Much after this epoch, the universe was almost neutral. Okay? Now, the origin of CMBR, as we see it today, is deeply related to this phenomenon. In order to see this, let us look at a space-time diagram. And to begin with, to illustrate the thing, let us consider a universe which has one time dimension and two space dimensions, so that we can draw it. Okay? So, there is this insect on a two-dimensional surface. This insect, very intelligent, but so we can do relativity in cosmology, but it cannot imagine third dimension. It knows length, breadth, and it has a clock to measure time. Okay? It does not know what is height. Okay? Its existence is purely so that we can explain it on a two-dimensional board. So before that, I should just make one comment about the line element which I talked about cosmology. See, I had said that ds square equal to minus dt square plus a square dr square by d. Now, if k equal to 0, then I can actually, what I can do is, I can make a change of this variable to a new variable eta, which I call conformal time, which is defined as d eta equal to dt by d. Okay? And then I can write this as ds square equal to a square minus d eta square plus dr square plus r square d omega square. Now, this portion is just Minkowski line element. It means that to begin with, for k equal to 0, I can clearly say, see that by the simple transformation, by in which I am multiplying a function with the Minkowski line element, I can get the line element for my case. These line elements in which one line element can be got by multiplying by a function of x mu times another line element. This is called conformal transformation. Okay, so conformal transformation as an, I mean here there is one confusion, this always have a problem, especially to particle physics when I talk about. When particle physics talk about conformal transformation, it's a different thing. Okay, particle physics say something about Weyl transformations, which is what is conformal transformation in for the cosmologists. Okay, so it is a transformation in which the coordinates are left untouched. On the same set of coordinates, you see, what is the role of a line element? The role of a line element is to define something called distance. Okay, distance in a more general way, including the ds square. Now, what is meant by defining a distance? It means you are prescribing a G mu nu for that space. Okay? So given a set of coordinates, you prescribe a G mu nu, you get a certain concept of distance. In Cartesian system, you prescribe the G mu nu of 1, 1, 1, and so you get Pythagoras theorem. However, if you want to go to the most general definition of distance, it basically says that a distance is a function of 2 points, which has the following properties. That is a positive definite function, which of course here it will be different because it's a pseudo-Riemannian. Okay? And it is symmetric in the 2 points. If I interchange these 2 points, the distance will remain same. Distance from A to B is same as distance from B to B. Then in a most general way of defining distance, there is nothing else about distance. The Pythagoras theorem of defining distance is one of the various ways in which distance can be defined. Now, given the set of coordinates, I can always be perverse enough to impose on it another G mu nu. And once I put another G mu nu, it will define another distance for me. Okay? These two distances will not be the same. And remember, this transformation is not a coordinate transformation. Okay? So, for example, if you take Einstein's equation and you do a conformal transformation, it is not invariant. It will change. Okay? Unlike the case of coordinate transformation. Okay? So this transformation is a conformal transformation. The only thing is that this f should not be 0 or infinity, because because the inverse should also be defined. That's all. If you look at this is exactly what has happened. This is the case of the Minkowski ds square. I have multiplied with a, which is a function of time. More generally, it can be x mu, it's a particular function only of time, and I have produced a new ds square. In other words, by this ds square has been obtained by a conformal transformation of a Minkowski ds square. Okay? Since this ds square is flat, this ds square is called conformally flat. Okay? So this is a conformally flat metric. So one thing which you can see very clearly and in a very straightforward way is that k equal to 0 is a conformally flat metric. Okay? However, one should remember one thing. In the case of k equal to 0, it can be seen almost in an obvious way that it is conformally flat. It turns out that even when k equal to plus 1 or minus 1, I can make a coordinate transformation from RT to a new set of coordinate transformation, some capital X, capital Y, in terms of which I can still write, even for k equal to plus minus 1, ds square will be equal to a square times some minus, I will put it dt square plus dx square plus x square d omega square. This is not the standard R or T. It is some transformation from RT to a new set T and X. However, this structure is such that in terms of T, capital X and theta and phi, this is a flat metric. Okay? And this may be a function of it. I'll just say a square. So this multiplied by this a square gives me the new metric. So this is true even for k equal to plus minus 1. So all what I am saying is that all the Friedman-Roberts-Nocker line elements are conformally flat. K equal to 0 can be seen to be conformally flat. Obviously, in the case of k equal to plus 1 or minus 1, you have to do some more hard work to discover this transformation. But all of them are conformally flat. Now, why am I harping about it so much? I am harping about it so much because once you have a metric that is conformally flat, you have a major advantage. This is the advantage. See, in a flat metric, when c equal to 1, the structure of the light cone, that is 45 degrees. Okay? ds square is 0. But if my Minkowski ds square is 0, if it is non-zero, then ds square for this and this will be different. But if this ds square is 0, anything multiplied to it is also 0. It means that if it is conformally flat, then the property of the 45-degree light cone is preserved, immaterial of what is the other coordinate system I choose, as long as it is conformally flat. So this helps me to draw the light cone structure, which will be important for my CMB. Okay, how the photon travels. So, in order to see some things in a very transparent way, it will be very useful to plot my photon trajectory in terms of these coordinates rather than the original. And that's why I am doing this. Okay?
Sorry, A still will be function of time.
Which one?
A square.
No, I am just wondering it's a function of, it will definitely be a function of time. I am just thinking it will be a function of x also. It's not a constant.
This time the universe has its own conformal time.
No, sorry, you're right. There will be some A tilde or something. Okay? I'm not sure about that, but this will be just a conformal transformation of this one. Sorry, what is it?
I was saying that the universe has its own conformal time rather than the usual time.
No, see, time is a coordinate. No? I mean,
Now
a clock which is moving faster is a different time.
No, you have transformed the usual time to conformal time. So now.
Yeah, so this is called conformal time. So, like for example, it is like this. I have one clock which has been moving in a certain way, right from the beginning of the universe. The other clock which has been slowing down as the universe expands. So that will be conformal time. Okay, so this is a transformation of coordinates, nothing else. All what I am saying is I can discover new set of coordinates where this structure is there. Okay, so this means that in the space-time diagram, okay, the moment I bring it to this form, my light cone structure will be 45 degrees. You had one lecture on inflation, right? Today morning? Horizon problem or something was done?
Actually, tomorrow I will discuss those things. Today I have recapitulated all this.
Oh. So maybe I'll be including slightly.
So there are lots of new things as well. So no problem.
Okay. Fine. So let us see in this diagram what happens to a photon in the context of what I was talking about, its interaction with matter and so on. So here I plot time. When I say time, I mean the conformal time or the other capital T, which for whichever there is a 45 degree thing. Okay? Time, space. And as I said, for convenience, I will take a two-dimensional space. Okay. And suppose this is the epoch which corresponds to recombination. That is, ionized matter becoming neutral matter, corresponding to the temperature of something like 3000 Kelvin. Now, as I said, before this epoch, the universe consisted of ionized matter. Okay, and as I said, the photon trajectory is like a Brownian motion. So now, suppose at some point there was a photon which started out after a scatter. Now, clearly, the only thing which the photon can do is to go along 45 degrees. The only freedom it has is that in this cone, whether it chooses this side or this side, but it has to be confined on the cone because it has to be a 45 degree. Okay? So it chooses one of the directions at random and it goes, and since time is always progressing, it will go along a 45 degree line. Okay? Now, in this, suppose I look at ionized particles, are all particles at rest. What will be their space-time trajectory? They will all be straight lines like this. Right? So as the photon comes, it will hit one particle here and get scattered again. But now when it is scattered, it doesn't have any information of what it did before. It's a Markov process. So it randomly goes into some direction along the light cone again, 45 degree light cone. Okay. Again it gets scattered and goes. So it means that it keeps on climbing this ladder in the direction of time along various cones. Okay. And what happens is, so this happens everywhere. What happens at this recombination era, I mean rather not this line but this whole plane, is that, now let us take a very, very oversimplified picture as if the recombination was instantaneous. Okay? There was an epoch where this photon got scattered for the last time. Before it got scattered again, the universe became neutral. I mean, it's kind of an oversimplified cartoon picture of the whole thing, but it helps to bring a point. Okay. So it gets scattered here, it would have got scattered by another particle, but before it reaches that particle, the universe becomes neutral. As a result, there is no more scattering. So the photon goes and then start, if it was moving in this direction, it continues to move in this direction. So in whichever, so if there is another photon moving in this direction, it will continue to move in this direction. So from here, the photons all will be going into an infinite 45 degree cycle. And this will happen at every point on that surface of last time. Okay, epoch of last time. Is this clear? Okay. See, it didn't happen now, but usually I tell in my class. And I'm teaching quantum mechanics after some 45 minutes, when people are all tired, and I ask, there's a complete silence. I tell them it is like All India Radio News. If there is a riot, and after 2 days of riot, they will describe what is the situation, they will make one sentence. The situation is tense but under control. Okay, so this goes along this 45 degree, like that it happens everywhere. And suppose this is my 2D. Now what happens, suppose there is this photon here. There have to be two conditions for the photon to reach me today. It has to be the right distance and it has to be directed towards me. So now, suppose I have a photon here. There will be a lot of, suppose I have a number of photons here, they are being directed in different directions in R. So they are all along different light, along the same light cones but in different directions. The one which is directed towards my point has the chance of reaching me. That is the one which I can see. But what happens is, say here, it comes here, but it has reached my point here in the past. So it won't wait. Okay? I mean, there's a time and tide wait for no person. Time, tide and photon waits for no person. Okay? So it just passes this and goes off. Okay? A similar thing which happened here, again, one of them must have been directed towards me, but it has not yet reached me. What reaches me is from a particular distance over here. The photons which were emitted from here were directed towards me and were at this distance are the ones which reach me. But this is not a unique point. Any point in a circular region here, from here the photon which is going here would reach. So I will be receiving the photons from a circle. There will be a locus of points from where I will be receiving the photons is a circle. Okay. Now, what is characteristic of this circle? This is the circle over which the photons which I received today got scattered for the last time by ions. So I can call it the circle of last scatter. Yeah, that's right. So I'm just coming to that. So now, this of course I have drawn time, but what is the perception of an observer? The observer will perceive that the observer is sitting here and the person being bombarded by photons from all directions. Okay? From a certain distance which corresponds to this distance. So the person will perceive the photons are coming from this circle, which is a circle of last scatter. In 3 plus 1 dimension, as he said, instead of the circle of last scatter, we will have a spherical surface of last scatter. Okay? And we are sitting in the center. Okay? But there is a catch. These photons are having a temperature of 3000 Kelvin. So not only it will be microwave background, we will become a cosmological microwave oven. Okay? With 3000 Kelvin photons coming in. Okay? Why doesn't it happen? Because as the photons are traveling towards me, the universe is expanding and the temperature is decreasing as 1 by E. And hence, today I get the photon at a temperature of 2.73 Kelvin. In fact, this is one of the very concrete things which can be ascertained. You see, that is the redshift at which photons decouple. Because you know from laboratory experiment the ionization energy. From Saha equation formula, you know when the transition could have taken place, what temperature. I know from observation what is the temperature today. So since I know the ratio of the temperature, I know the ratio of the scale factor, today and then. So I know the redshift exactly. Okay, so this can be exactly be calculated. So this is the, and this thing which I am receiving today, this photons from this apparent circle of last scatter or surface of spherical surface of last scatter is what is cosmic microwave background radiation. Now, I mean, it may be obvious, but I just wanted to make it clear that there is nothing special about this. If there is an observer sitting here, this observer will have his or her own spherical surface of last scatter. Okay? So in the sense that if I am observing it today from here, or you are observing it from there, we will be seeing two different spherical surfaces of last scatter. But I mean, assuming you are in the next galaxy, or I am in the next galaxy. Okay? But although we are looking at two different spherical surfaces of last scatter, since the universe is homogeneous and isotropic, the statistical properties of both these spheres will be the same. Okay, although the spheres are different. Okay, it is again the example which I gave about a lawn. A well-maintained lawn, whether I measure the greenery here or here, it is the same. Although there are two different patches of the lawn. Okay.
But here in this diagram we already have a predefined time and space structure. In extension of the universe we don't have a
No, but you see, time and space is actually not something which you directly measure. See, anything which is a coordinate, you never measure. You see, for example, okay, just to give you, when you want to define velocity, it is not dr by dt. Okay, it will be the value of ds at t equal to constant divided by value of ds at r equal to constant. Okay, so since ds is a scalar, I mean, it won't matter what coordinate I use. Okay. Okay, so one thing which we see is the following, that because there is no scattering after the surface of last scattering, by its very definition there is a last scattering, the photon will travel unhindered. And that is why I said that photon carries the information about an early universe without getting destroyed. Okay. However, there are a few ifs and buts there, which I will come to. There is of course another bonus over here, right? Just now I talked about homogeneous isotropic thing, you know, like the surface of last scattering. Now, how does the photon carry information about perturbations? Let's go back to the same diagram. This is R, and this is my surface parallel to it at a recombination. And this is today, and I am receiving the photons from here, or alternatively, I am sitting here and receiving the photons from this spherical surface of last scatter. Now, the universe, although we say homogeneous, isotropic and all, we see that there is structure in the universe. So the question is, how does this structure form? Okay, and that's what will be addressed in inflation or perturbation as well as structure formation. What I will just say is the following, that the way structures are supposed to have been formed is, okay, so before that I should give this example. Suppose I take a uniform plasma, okay, or yeah, I have a uniform plasma. Now what I do is, I increase certain amount of positive charge at some point. What happens? How does the potential go because of that in distance? 1 by? It's not 1 by r. It is a Debye shielding. E to the power minus alpha r 1 by r. The effective potential. And that happens because when the positive charge gets here, negative charges crowd around and shield the potential. Another thing which happens is, if suppose I have just not plasma, but a uniform distribution of charges. See, plasma would mean there is overall neutrality. Suppose I don't have that, I just uniform distribution of charges. I increase the density of charge at one point. How will the system react? Because of repulsion, they will be driven away. So in other words, any disturbance to the uniform charge distribution, there will be a restoring force to restore it back to the initial uniformity. Both these things get violated in gravity. You may wonder that Coulomb's law also is 1 by r potential. Gravity is also 1 by r potential. Why does this happen? It happens because of two main differences between electromagnetism and gravity. In electromagnetism, there are two kinds of charges, plus and minus. In gravity, there is only one kind of charge, positive mass. There is nothing called negative mass. And the second aspect is, in electromagnetism, like charges repel. Positive charge repels positive charge. In gravity, like charges attract. Positive mass attracts positive mass. Because of these two, both these things get, both these effects are there. So what happens is, in the case of Debye shielding, because of the increase of charge, there is e to the power minus alpha r by r. Because of this special feature of gravity, where there is only positive mass, okay, this basically becomes a complex number. So that's why when you have gravity, okay, and there is an extra gravity thing, the distribution function has oscillatory features. Unlike, so this becomes an e to the power minus I something of that kind. So there is an oscillatory feature in the case of gravitational perturbation, whereas in electromagnetism is exponential. The other thing is, in the case of electromagnetism, since the things repel, it is restored to the original homogeneous distribution. In the case of gravity, since the positive mass attracts positive mass, the moment you have an extra mass, there is more gravity. More gravity means it will bring more mass, and hence even more gravity. So it goes into an unstable runaway situation. And it is believed that this is how galaxies are supposed to have been formed, in a very zeroth level picture. There are other problems like, expansion of the universe, pressure of matter and so on, but okay, basically it is gravitational collapse. The moment it is able to overcome all the others, it will form galaxies. Okay. Having said this, there is just one issue involved. If I have a completely uniform distribution, it will remain uniform. The thing will start only if there is a non-uniformity built in. How does it build in? That's what I think he will talk about, as to how the original perturbations are created by quantum fluctuations. Okay. So, the reason I am mentioning is, or what I am saying is, so suppose everything was homogeneous, then you will have the world length of all the particles, they will have a uniform density everywhere. In any small region, the number of particles will remain same. It's a uniform density. However, if there is a non-uniform density, there will be more number of particles here and less number of particles here. Okay? Now, so what happens is, when you look at it from the top, all the particles are word lengths coming out. In some region there is a higher density of word lengths, in some region there is a lower density of word lengths. Whatever word lengths are here, I don't have information about it, because light from here has not yet reached me. Whatever word lengths are here, the light has already come and gone. What I am receiving is the density of word lengths on this circle. So on this circle, suppose there is a high density of word lengths here and a low density of word lengths here, then I will find that when I am looking at it these two directions, I will find that there is more scattering from here and less scattering from here. Do you get this point? You see, I am sitting in the center of the circle and I am looking at the circle. The inhomogeneity in the space is converted into anisotropy when I am looking at it. You see, because this region of the circle, the photons are scattered more, because there are more charges here. Here the photons are scattered less. Okay? So there is a difference in the nature of the distribution of photons here and here. So when I am looking at it from here, something is here and different thing is here. So in other words, as I scan this entire 2 pi angle, there is an anisotropy. And this is how the inhomogeneity in the universe is getting translated to the anisotropy in the microwave. Okay? So, so it is like this. So I have inhomogeneous thing, but now what I do is I don't look at the entire thing. I scoop out a spherical shell and I take out the spherical shell. And in CMBR, I am just looking out what is on the spherical shell. So that when I am looking from the center, there is something here and something here. So that is anisotropy. Okay, so this is the origin of anisotropy. However, this anisotropy, this is not the only reason why anisotropy happens. There are various other reasons which I come to in detail. Okay? But all what I am trying to say is the inhomogeneity in space-time or matter, okay, gets translated to anisotropy in the microwave. Do we stop now? So tomorrow I will take these three aspects of anisotropy, polarization and distortion of the spectrum in detail.